Before I talk about the second alignment method, I want to go over some important properties of pairwise alignment. Remember in the brute force alignment session, we have learned that there are only two possible ways to align bases, either align a base to another base or align a base to a gap. So given two bases, there are only three possible ways to align them. Either align these two bases to each other, or align one base to a gap, or align another base to a gap. So that is similar to the direction in the dot plot. Either go to the diagonal direction, or go to the horizontal direction, or go to the vertical direction. Okay, another important property is that the best alignment is equal to the current, the best alignment in the previous position plus the best alignment at the current position. So seeing this equation, I think some students who have computer science background would have already know the title of my next slide. That's right, it's dynamic programming. Dynamic programming solves problems by combining the solutions to sub-problems. It's a computer algorithm used to solve optimization problems with optimal substructure property. What is an optimal substructure property? It means that the combination of local optimal solution is the global optimal solution. So in another word, good plus good is good. The basic idea of dynamic programming algorithm is to divide a complex large problem into several small problems. Then, by finding the optimal solution for these small problems one by one, the optimal solution of the original large problem is finally solved. Now, let's take a look at how to use dynamic programming algorithm to solve our alignment problem. It is similar to the dot plot approach. One sequence is placed in the column and another sequence is placed in the row. Instead of placing a dot in the grid, we compute a score for each position, and then we find the path through the grid with the highest possible score. That is the optimal alignment. So here, I show different passes. The first one is the diagonal path, and it shows the two sequences are aligned to each other. Three of the bases are match, and one of the one position is mismatch. And in the alignment 2, the vertical line indicates a gap in the horizontal sequence. And similarly, in the alignment 3, a horizontal line indicates a gap in the vertical sequence. Next, I will talk about the famous Needleman watch approach for global sequence alignment. It contains 3 basic steps. First, set up an alignment matrix or dynamic programming matrix. Here, this matrix looks very similar to the dot matrix. However, the first row and the first column are empty. It's saved for the gap. The second step is get the score into the matrix based on some substitution matrix or scoring matrix. The third step is to identify the optimal path through the matrix. And I strongly recommend you to read this paper published by Needleman and Walsh in Journal of Molecular Biology in 1970. Next, I will use a protein sequence as an example to demonstrate the Needleman-Walsh algorithm for global alignment. Even though nowadays DNA sequence is far more than protein sequence, actually the study of sequence alignment started with protein sequence. Remember the paper was published in 1970, and the first DNA sequencer, Sanger DNA sequencer, was invented in 1977. So Here I use a very simple scoring matrix or substitution matrix for the calculate the score. The match is +1, mismatch is -1, and the gap is -2. For the gap penalty, I didn't differentiate the gap opening versus gap extending, and just used the simplest linear gap penalty -2. So talking about the substitution matrix or scoring matrix, for proton, Margaret Dayhoff constructed the PAM matrix. It's the most authoritative substitution matrix in life science since 1978 and was replaced by the Blossom matrix in 1992. Now, most methods use Blossom matrix. Okay, let's start our alignment process. It always start from the upper left corner in this cell, and the score always start with 0. If we go from the left to right, it's corresponding to the gap with length 1, 2, 3, 4, and the score is equal to the sum of those gaps, or the gap penalty times the length of the gap. And here those arrows show a path of or alignment. And here is its corresponding alignment view. So sequence 1 is aligned to 4 gaps of the sequence 2. Then let's go to the empty corner cell, the orange color cell. The value of this cell depends on its 3 neighbors. The diagonal one can be represented in mathematics by this format, and the upper one is this one, and the left one is this one. So which one is the maximum of these 3? 0 is the maximum, but we have to compare all the summations. So this formula is a very famous Needleman-Walsh algorithm formula. Let's calculate each case one by one. The first case is the corner cell. Here it has a score 0. And then from this one to the orange cell corresponding to a match between D and D. So the match have a score -1. So this one is 0 plus -1. Then we look at the upper cell. From this upper cell to this position is corresponding to a gap. And we need to add -2 and the gap penalty. And similar for the left cell. From left cell to the orange cell is go horizontally, so it's also corresponding to a gap penalty. Then when we put all those numbers, scoring numbers, into this formula, the first direction, diagonal direction, corresponding to score 1. The vertical direction corresponding to score -4, and the horizontal direction corresponding to a score -4. And we compare these 3 situations, and we know the first one has the highest score, and we put 1 into this orange cell. It's corresponding to a D to D match. We do the same thing for the next cell in orange color. Now its neighbor become to these 3 cells, and in the first direction it goes to -2, and the P and D is a mismatch, so this time it's a -1, and we got the score -3. Then vertically from top to bottom, we go from -4 to, since it's a vertical direction, it's corresponding to a gap penalty, so we get a score -4 plus -2 -6. And similarly for the go from the left to right, we also add a gap penalty and get the final score -1. So now we compare these 3 scores. -1 is the highest. Then we put a -1 into this cell, and we trace back. How did we get -1? It's from 1, and how did we get 1? It's from 0. So that is those errors is the pass. Then the third orange cell. So same, we just we don't look at anything else, just look at the 3 cells around this orange cell. Diagonal direction -4, and the mismatch L and D mismatch -1, -5. Horizontal direction -6, gap -2, -8. Or vertical direction. Horizontal direction is -1 and -2, -3. Again, -3 has the highest score, so we put a -3 here and put an arrow. Like remind us, how did we get -3? It's from the left cell, but not the other 2 neighbors. And that is the corresponding alignment view. Then we do the same thing, finish the second line, and then we go to the third line, third row. And for this orange one, its diagonal is -2, and the vertical is -5, and the horizontal is 0, so we put a 0 here. And this orange one is not listed here. Oh, this one should be 1. 2 plus -1 should be 1. Next, I will use 2 protein sequences as example to demonstrate Needleman-Walsh algorithm. Even though nowadays DNA sequences are far more than protein sequences, however, the study of sequence alignment was actually started for protein sequences. The Needleman-Walsh algorithm was published in 1970, and the first DNA sequencer, Sanger DNA sequencer, was invented 7 years later in 1977. And 1 year later, in 1978, Margaret Dayhoff constructed the PAN matrix, which is the most authoritative substitution matrix or scoring matrix in life science since 1978, and then was replaced by the Blossom matrix in 1992. So nowadays, most methods use Blossom matrix. Here, for simple, I just use a very simple scoring matrix, match equal to 1, mismatch equal to -1, and the gap equal to -2. I didn't differentiate the gap opening versus gap extending. It's all use a linear gap penalty, -2. The alignment always start from the upper left corner, and the alignment score always start with 0. And then we go from left to right. That's corresponding to gap with length 1, 2, 3, 4, and the score is the summation of the gap penalty. And here, those arrows shows a path or a alignment, and its alignment view is shown here. So sequence 1 corresponding to 4 gaps in sequence 2. Next, let's look at this orange cell. We always start from the empty corner cell in the upper left, and we look at its neighbor. The diagonal direction is either a match or mismatch. In this case, D and D is a match, so it's +1, and the horizontal and the vertical corresponding to gap. So here, I listed the formula, the very famous formula for Needleman-Walsh algorithm. It considers 3 situations. The first one is the diagonal direction, is the previous cell plus a match score. And the second line is the vertical cell plus a gap penalty, and the third one is the horizontal cell, the horizontal neighbor plus a gap penalty. Now let's put in all the numbers. So the diagonal one is number 0, and here is a match, so it's +1, we got 1. Then vertical direction, we got -2 plus -2, -4. Horizontal direction, we got -2 plus -2, -4. And comparing the results, 1 is the maximum, and this is got from the diagonal neighbor. So we put an arrow here, reminding us this one comes from 0, and this one corresponding to a DD match. Here is the alignment view. Next, this orange cell, it also has 3 neighbors, and the diagonal neighbor gave it a score -2, and the P and the D is a mismatch, give it a mismatch score -1, give it the final score -3. Similarly, the vertical neighbor and the horizontal neighbor gave it scores -6 and -1. And comparing these 3 numbers, -1 is the maximum, so we put a -1 here and use an arrow to label. This -1 comes from its left neighbor. So similarly, we put a number, the highest number, highest score -3 into this orange cell, and this is its corresponding alignment view. After we finish the second row, we start from the top left corner cell and do the third row. And for this orange color is from the horizontal neighbor, and we put an arrow here. And after finish the third row, let's do the fourth row. This orange cell comes from its diagonal neighbor. And finally, we finished all the matrix, and the score of the best alignment of the entire sequences is stored in the right bottom corner, this cell, the score in this cell. For this one, it's 2. And how did we get 2? Let's trace it back. The 2 comes from the 1 here, and comes from the 2 here, and comes from the 1 here. So the alignment has no gap in it. It's just the base-to-base alignment. But please note here, the optimal alignment is always dependent on the alignment score or the scoring matrix or substitution matrix we used for this alignment. Later on, I will show you an example. Yeah, this is the example. What is the optimal score for the alignment of these sequences? Okay, yes, it's the right bottom corner. The score is 2. And how did we find the optimal alignment? Let's trace it back by using those arrows. This one, 2 comes from 1, and 1 has 2 arrows pointed to it, so it has 2 passes. One is from 3 to 2, the other one is from 0 to 2. So here the 2 different alignments or the 2 different passes are showing different color, red and green. So which one is the optimal alignment? The answer is both of them are the optimal alignments. So it's not a unique solution. Also, the alignment and the score are dependent on the scoring system. If in the scoring matrix before we increased the gap penalty from -2 to -3, then the final optimal alignment will be the blue color one. And the final optimal score is 1 but not 2. And we can see because we increase the gap penalty, the final alignment result has no gap in it.